So Sankey diagrams are just ways really of showing efficiency in a more graphical manner, and they're quite useful because they make things a lot easier to understand because you can visualise what you're seeing. So here I've got two Sankey diagrams, okay, so we're going to describe, you can probably work out how they work from here, but we'll describe how they do anyway. This is for a filament lamp and this is for an energy saving lamp, and if we remember from the last video, the difference between these two is that filament lamps are much less efficient, they use much less energy usefully, they waste much more energy, okay. Now a Sankey diagram tells us about how much energy goes in and how that energy is used. So for both sides of this, or for both types, we start with electrical energy and we're going to write 100%. Okay, so they all use completely electrical energy, they don't use anything else. So it has to be 100% to start with because you can't start with anything less. Now, a filament lamp only uses 20% of its energy as light. And the other 80% is wasted as heat. And this diagram shows that, and you can see that this branch is about 20% if this is 100%, and this branch is about 80% here. Now it should be exactly, but I haven't used a ruler, so it's not completely perfect. Okay, so the size of the branch shows you proportionally how much energy is being used. So I've got a rule down here: the bigger the branch, the more energy it represents, and it should be done quite carefully. So normally in an exam you get given a grid to draw this on, so you can definitely count squares and make sure your area is completely right. Another convention is usually waste, so it's, waste energies go down. Waste goes down, points downwards. Okay, now that's not always followed, so I wouldn't get too hung up on it, but often the waste energy is pointed down. So if we compare this to this, if we compare the filament lamp to the energy saving lamp, we can see now already the difference between them. Okay, so if the waste energy goes down, we can see that the one pointing down is much, much smaller. So we know already that it wastes less energy. Okay, so here we'd have to write down that the light energy, we know it's 90% efficient, so light is going to be 90%, and that heat is only 10%. And that's why this arrow here is smaller than that arrow, because this arrow should only be about 1/10 of this width. Okay. Now, the total width remains constant. If I had a 100% efficient light bulb, it would just go straight across, or if I added that into there, it should be about the same width. And that's because it's telling us that energy can't be created or destroyed. It's the conservation of energy, which is something you might have heard of before. So you can't make energy out of thin air. It can't just disappear. It has to be converted. Now a lot of it's converted as waste, which we know, but it can't just disappear out of thin air. So Sankey diagram shows me graphically how much energy is wasted. Now we can do it in percentages, or we could write it in terms of joules or watts. So let's say that this lamp uses 50 watts of power. This would correspond to 10 watts, and this would correspond to 40 watts, because 20% of 50 is 10, 8% is 40. If we do 10 plus 40 equals 50. Okay. If we had the same one here, 50 watts, this would mean that this was 45 and this was 5, because 10% is 5, 90% is 45, add them up, it gets to 50. We could also write it in terms of joules. So let's think about in an hour, maybe not an hour, maybe more like 10 seconds, this would use 500 joules of energy. This would become 100 joules, and this would become 400 joules. So you can write it in terms of percentages, watts or joules, it doesn't matter as long as you're consistent. So let's look at a problem that uses Sankey diagrams, which something similar might be presented to you in an exam. So we've got here a car. Okay. Now the car uses 600 joules, I'm going to say per second. It probably uses more than that, but I've just made this one up. 120 joules are converted into KE. 130 joules are converted into sound. So we need to work out now how much is converted into heat. Okay, so 600 joules is the energy in, total in. Now we know that KE is the useful energy because we want cars to move. This kinetic energy, it's movement energy. So this is the useful energy. We also know that this and this, sound and heat, are both waste energy. Now you know that A because it's common sense about a car, but B because they're pointing downwards, so they must be waste energy. Now the total energy in can't disappear, so 600 joules has got to equal 120 plus 130 plus whatever this is. So you can work out what the heat must be. So 600 equals 120 plus heat plus 130, which is equal to 250 plus heat, which is equal to, that means that 600 minus 250 equals the heat. So the heat energy is equal to 350. All I've done is done a kind of blank thing there, so I could have worked out with all that without all that rearranging. So 350 joules are wasted as heat. Now what often happens is you'll be asked to use this to analyse a situation and work out the efficiency of a car, okay, or another device. So remember from our last video that efficiency is this. Efficiency is useful energy out divided by total energy in times by 100%. So the useful energy, efficiency, is the KE. That's 120 joules. The total energy in is at the start. It's the chemical energy from the petrol. That's 600. And we times that by 100%. Now, this is another one that I should be able to do in my head, but I've forgotten. So I'm quickly going to do it on a calculator. So 120 divided by 600 gives me 0.2 times 100. And that is going to be the same as 20%. So this car is 20% efficient. It wastes 80% of its energy. So this is an example of a quite typical problem you might get given in the exam. And you need to know how to use these things and how to analyse them to answer this type of problem.